All right, everyone, come in, sit down, find a seat. There was a very strict sign on the board about a checkerboard pattern that appears no one has seen, so I'll just let you go for now, but in future there's a sign on the door that says sit in a checkerboard pattern. Hello, everybody. Welcome to the Astronomy Colloquium. It's my pleasure to introduce Dr. Jackie Faherty. She is a senior scientist at the American Museum of Natural History, cross-appointed in the astronomy and education departments. She's an expert on brown dwarf and exoplanet atmospheres. We are going to see some Cycle 1 JWST data that no one's seen before. I'm really excited. You have to stay to the end. She is also an excellent public speaker, so no pressure, but we're expecting a really good talk. And if you read the New York Times, was recently profiled in Sunday's New York Times. So if you want to know more, go to the New York Times and look up Jackie and can read all about how she watches the sunrise from her beautiful terrace in Harlem. So please join me in welcoming Dr. Jackie Faherty for her colloquium on brown dwarfs. Thank you, Jackie.
I'm going to set this thing up. Oh, this is a nice crowd, and I want to encourage people to interrupt if you want to. I gave this talk at NYU last week or the week before, and they interrupted about 80 times. So the bar is high, and it was so many interruptions that I got 3/4 of the way through the talk, and it was like, time's up. And I was like, all right, the last part of this talk is to show you some JWST data, but I have no time. And they were like, my God, you have to keep going. And I was like, fine. So I will say the same thing to all of you. At the end of this talk that Jesse just alluded to, I'm going to show you some hot off the telescope, fresh from the telescope, some of which came in last week, data and brown dwarf experts coming in the room. And this is a nice crowd, so just interrupt if you want to. And it will hopefully get you excited about these little objects called brown dwarfs and convince any of you that may or may not be on a time allocation committee why you should give a lot of time to brown dwarf science in the very near future. Just saying, I don't care if you plug my proposal, just plug somebody's brown dwarf proposal. So here we go. Brown dwarfs. What are they? They exist in between stars and planets. So in some ways, they defy definition. Most people identify this as a star, a compact source that is got a hot enough core so it can get nuclear burning going. Stars are well defined because they join a main sequence. They remain at a temperature, roughly the same temperature, for billions of years. They can be fairly stable when they're on the main sequence. All of these things about stars are great. Planets, on the other end, we can identify as being quite opposite. No one really debates Jupiter as a planet. Jupiter, of course, it orbits the sun, probably formed in a disk around the sun as far as we can tell, but it does not have nuclear burning at its core. So brown dwarfs are these objects in between stars and planets. They come in at about 75 times the mass of Jupiter when you can't squish the material tight enough in order to get nuclear burning in their core. So instead, they just cool through their lives, morphing from looking somewhat like a star, a low-mass star, through billions of years, morphing into looking more like Jupiter. So these objects change throughout their lives. They never really look the same depending on when you're looking at them. They're excellent at hiding their age. They're excellent at hiding their mass. So there's something called a age-mass degeneracy that exists for these things. And I'm going to just zoom in on this, on the kinds of brown dwarfs that you can get. They span in spectral class from late type M's down through the L dwarfs, T dwarfs, and Y dwarfs. These are all the letters that we use in brown dwarf science. And they start as hot as 3,000 degrees Kelvin or so, and then they morph through these other temperatures, 1,500 to 1,300 degrees Kelvin for the L types, which I'll spend a little bit of time on L types today, 500 to 1,500 degrees Kelvin for the T types, and then down to the coldest temperatures of these objects, as low as 250 degrees Kelvin. I'm going to repeat that number again. 250 degrees Kelvin. That's just 100 degrees Kelvin warmer than Jupiter. Brown dwarfs span from stellar-type temperatures all the way down to basically Jupiter. So you get an enormous amount of chemistry, rich chemistry that these objects can span. They can have their fantastic laboratories for looking at atmospheres. And while they are not planets, although I'm going to dig into that question in a second, they are comparable in their features in these temperatures for every single solitary directly imaged exoplanet that has ever been looked at. Every single directly imaged exoplanet, and I know many people in here are involved in direct imaging campaigns, every one of the direct imaging campaigns that's made a discovery that has glossed the pages of your newspapers has been at the exact same temperature of a brown dwarf, for which we have beautiful spectral energy distributions, amazing amounts of data. And this is why I hope I'm going to pitch you like crazy on why we know so much on these objects, and they have to, absolutely have to be utilized in any exoplanet study that exists. So they're largely found in isolation, and this is a compilation of brown dwarfs that are very cold, more on that very cold 250 degree Kelvin that I was freaking out about a little bit temperature-wise. And these are little cutouts here, about 90 arc seconds on the side, from a little tool called WiseView that was developed by a citizen scientist named Dan Castledon that's been working with myself and Davy Kirkpatrick and Federico Morocco here on a project called Backyard Worlds: Planet 9, which is this citizen science project that we've been working on for several years to try and uncover close by cold brown dwarfs near the sun that had been previously undiscovered. Now, all of these are jumping around. You can see we find them in isolation. They separate themselves off. You can just look at them with a wide field survey like WISE. They pop out. These are really cold. There's a couple hundred degrees Kelvin. By the end of the talk, I'm going to show you some data from JWST on these objects. But this slide is basically just to show you that we largely find them in isolation. And so nobody's really talking too much about the word planet with them because they're in isolation. But then there's these guys, which are brown dwarfs that are dancing around with a star. And so you do find them now at colder temperatures or lower masses orbiting a star. So in this case, this is another blinking of images from the Wide Field Infrared Survey Explorer over several years. So you can see objects jumping. Here's a star, an early K dwarf, and this little jumping dot with it, an L8. And in each one of these cases, you can see there's an object jumping around with the star. So we also find them widely separated from a star. Every now and again, you find them pretty low mass orbiting a star. So there's this open question that I'm going to just keep digging into. What is the difference between a brown dwarf and a planet? What is the difference? Is that even a meaningful question to ask? I made it seem like I could define them for you. They don't have nuclear burning at their core. Fine. That makes them easily differentiable from a star, but planets don't either. Are you going to try and use mass as the differentiating factor? Okay, so what boundary are you going to use? Possibly 13 times the mass of Jupiter, because that is when deuterium burning, stable hydrogen, deuterium burning, it's not stable hydrogen burning, but it can exist for a little while in brown dwarfs. Planets can't get that at 13 Jupiter masses, maybe. If that's what you want to use as your definition, but it's a terrible definition in some ways, because every now and again you find one of these things orbiting a star. What should we use as the definition? Possibly formation mechanism. How did it form? Do you form through a giant molecular cloud collapsing and fragmenting off into small pieces? Or did you form in a disk around a star? I just showed you two cases. Brown dwarfs are found both isolated and orbiting a star. So that leads me to this plot, which is one of these very famous exoplanet plots. You can pull a lot of this information off of NASA's Exoplanet Archive. And it's showing you the separation of a system, the semi-major axis in astronomical units on the x-axis here, and the mass ratio of a system. So the mass of the secondary over the mass of the primary. So the bulk of the objects that you see on the far left-hand side here are going to be from the exoplanet archive, and I have them color-coded by the detection method for which they've been discovered. Now on the upper area here, this big blob of purple, these are stellar binaries, or I'm giving you what I think is happening. These are near equal mass ratio systems, because this is mass ratio here, that are very closely separated and widely separated. So in the case of a plot like this is 1 astronomical unit here. Walk yourself out in separation. You're at a Saturn-type distance, a Pluto-type distance, Oort cloud, and then an irrationally large distance away from each other. What you can see, the bottom left corner of this kind of plot of companions should let you argue that whatever system you've discovered here is probably an exoplanet companion, because you've probably easily formed this object in a disk around the higher mass companion. Way up here on this corner, you've got what you would call a stellar binary, because you've got 2 objects of the near equal mass very widely separated from each other. But after study after study after study, direct imaging, brown dwarfs, we've found this area of objects that I'm just labeling as transition objects that make you scratch your head and beg the question of what's the formation mechanism of the objects that are in what we also in my group lovingly call the highway, a highway that exists possibly in between the stellar binaries and the exoplanet companions. So even if you wanted to make some claim of using a plot like this as the differentiating plot for a brown dwarf companion versus a planetary companion versus a stellar binary, you still need a little bit more information before you could convince somebody. And the holy grail that many people turn to is the carbon to oxygen ratio. So if you could access what the carbon to oxygen ratio was for all of the objects in here, you would be able to say something, potentially, about where the object formed. If it formed within a disk, you might expect that it's going to have an enhanced carbon-oxygen ratio compared to a primary, because where it formed in the disk was probably beyond an ice line, where the oxygen gets sequestered, and then you end up getting a higher carbon-to-oxygen ratio. If it formed similar to the way the host star formed, you would expect the source to end up with a solar-type carbon-to-oxygen ratio. So that leads me to part 1 of this talk, which is on chemistry. Can we assess the bulk chemistry of brown dwarfs, and can that bulk chemistry differentiate the formation pathway? In the era of JWST, you hear this left, right, and center. There's about 80 proposals I know about that people are pitching left, right, and center to go after the carbon to oxygen ratio of a companion to determine how it formed and define the system. Well, I'm going to show you the work that we've been doing that's going to make people, I hope, think harder about how the claims of carbon to oxygen ratio should be considered. So the object that I'm going to now dig into as the example is the first brown dwarf ever discovered. It's called Gliese 229b, and on this particular plot, it sits pretty high in what I was calling the stellar binary area up here. It's closer to what I was calling the transition area in here. This is where it lives on this particular plot. So here's what we did. We have a lot of data on this system called Gliese 229b. It's a T-type object. Here's the spectral energy distribution for it. This is wavelength on the x-axis here, from optical wavelengths all the way out to almost the mid-infrared wavelengths here. This is the flux on the y-axis here, and labeled for you are the prominent absorption features that we see. Brown dwarfs are not black bodies. They have an enormous amount of molecular absorption that comes. And what you'd like to do is not just label where these features are, but actually measure what the abundances of the various molecules are so you can back out a bulk chemistry for the source. This is going to be a highlight of my graduate student, Emily Calamari, and I'll just point you to the paper that we have on this. Is actually on the archive as of last week, so you can look into all the details of this if you want to. Okay, so we dug in to Gliese 229b, which has a dynamical mass measurement, which could be a completely other colloquium because it's a pretty heavy T-dwarf, which makes us scratch our heads. And we used a technique called Retrievals, which I know several people in this room are working on as well. So we used this technique, also referred to as the spectral inversion technique. So a second on retrievals, even though I know several people in here know a lot about retrievals. When you're fitting the model, when you're trying to fit an object, you get your spectrum, you get a lot of photometry, you get a beautiful SED, and you want to back out the fundamental parameters for it, you kind of have two choices. You can turn to what's called the self-consistent grid models, where theorists have sat down and used accurate laws of physics and chemistry and grinded out a grid of models across what they called reasonable chemistry, reasonable C to O ratios, reasonable metallicities, reasonable gas opacities, and they give you that data and you just fit. See how your data fits it. On the opposite end, with a spectral inversion technique, the data is the input. You take the data and you say, here's the chemistry, here's the physics, I'm going to cook it up with this data and see what the results are. And in that way, there's pros and cons to both. In this way, you're able to have a far more flexible temperature pressure profile. You're able to also solve some incorrect physics a little bit. That can happen when you do the spectral inversion technique, but it allows you to do things like parametrize the clouds in an object, which you can't do really with the forward grid model. There's a lot of codes out there for doing the spectral inversion technique. The one that my team uses is called Brewster. It was written by my very close friend and colleague, Ben Birmingham, who's at the University of Hertfordshire. And this is not an acronym, so I shouldn't have capitalized it. It's the name of his dog. So it's not open source yet, but it's soon to be open source. We've written several papers using the Brewster code on brown dwarfs. And so I point you to two major ones. One is the original paper that introduced Brewster, and one updated paper that we called Cloud Busting. This is a phenomenal paper I could point you to, as well as several papers that were written by my former grad student, current 51 Peg B fellow, Eileen Gonzalez, on several objects that I would point you to. We use Brewster on several brown dwarfs in order to try and back out the chemistry of objects to try and figure out exactly where these brown dwarfs came from. And I want to point something out that I think is very important for anybody that does retrievals. This is my retrievals team, and we're a pretty big crew of people trying to use this technique. Two of the most important people in this crew are Shannon Vischer. I think I may have lost this. Oh no, it's here. Shannon Vischer here, and Marina Gemma. And the reason why they're two of the most important people on here is because they're chemists. And if they weren't there, we'd be solving for a lot of incorrect stuff, which we were. You can come up with a lot of interesting clouds that you can stick in one of these objects that will reproduce your data that is just completely unphysical chemically. But a retrieval just wants to see the best fit. So, word of caution. Shannon's always helping us figure out what we may or may not be solving here. All right, Gliese 229b, first brown dwarf discovered, methane-bearing brown dwarf. Here's some of the results we had. Here's the black is the actual data. The black is the data here. I showed you this before in an SED, and it's now broken up into two panels with just the near-infrared and what we call the extended data or the mid-infrared data. Those same chemical absorption features are labeled: methane, carbon monoxide, water. as dominant features, and overlaid is the retrieved model on top of it. So we put a little bit of a kitchen sink of attempts to see what kind of chemistry we could throw at this thing to solve for the bulk chemistry. And the results were the following. Our best fit model came out as cloudless. It didn't look like it had a cloud of note. And we were able to constrain the following gases: water, CO, methane, ammonia, and sodium plus potassium. So all of that was constrained within our model. And from those constrained gases, we were able to extract the carbon to oxygen ratio. And it's a co-moving system. Gliese 229A is co-moving, Gliese 229B is co-moving with an M dwarf, for which a C to O ratio was measured, which you can see over here is near solar. 0.68 is pretty close to a solar C to O ratio for the M dwarf. It's a little bit high, but still near solar. In the case of Gliese 229B, it came out almost twice the primaries. Now, we thought about this for a really long time. In some ways, one would look at this and decide, oh, look at that, smoking gun. C to O ratio is high. You must have discovered an object that was formed in a disk around, so you got a planet there. Absolutely not. That's a terrible, terrible thing for us to think, because this thing is a very big T-dwarf. You saw where it was living on that plot. It was up high by the stellar binaries. And so we wanted to investigate this a little bit further. We tried many models to see if it was something wrong with the gases that we put in. Was there something we weren't properly constraining? But ultimately, what we were able to conclude here is that the problem was actually not with the carbon. The carbon was matching the host star. The problem was with the oxygen. We had some sequestered oxygen. And we wanted to look at this really carefully and figure out where that oxygen might be. And we also wanted to check if this was a thing for retrievals. And so here's a plot that shows you other companion systems that have been retrieved. This is the full suite of retrieved companions of a directly imaged exoplanet or a brown dwarf, where the x-axis here is the separation of the system, and the y-axis here is the carbon to oxygen ratio. And then in the big bold letters here is each one of the objects. And so we show you both the primary, for instance, Gliese 229B with its super enhanced C to O, and Gliese 229A, which is a bit more than solar but kind of still within it. And you can see that in the case there's one or two that are straight on the line. HR 7672B looked good. HR 8799C sat on the line, both of them. But then there's a couple that were pretty far off. HD 3651B, for instance. And we thought, that's weird. There are a couple that do look like they're a bit enhanced. And then we said, let's just grab every retrieved object that's a brown dwarf and see if there's something to the C to O ratio, because I don't think anybody's plotted this all together yet. And so we made this plot, which shows you a retrieved temperature versus the C to O ratio. And now in blue are all of the isolated brown dwarfs that have been retrieved, and in green are the companion objects. And then Gliese 229B is here at the center here. Solar C to O is here. A lot of enhanced C to O in here. Now one could look at this and say, well, everything that formed above the line then we're going to call a planet because it's got an enhanced C to O ratio, and all the things close to the line are going to be companions that formed the way stars do. But that's clearly not a great conclusion. So what we're concluding is that, like I said with Gliese 229B, the carbon was okay. The oxygen is the problem in that case. How do you have an oxygen problem? Where does the oxygen go? The oxygen goes into clouds. Yeah?
In the other cases where you have the
We didn't actually look at where with the, because not everybody showed the analysis like we did. We'd have to go back and pull the primary data as well and see if their carbon was also the same. Because not everybody gives you what the carbon is in their companion. We give it in our paper, but we have to ask everybody to say, like, show us separately carbon and oxygen. That's part of our advice. Give us both so that we can check. Because oxygen is, where do you have oxygen? It gets lost in the clouds. You can have a mystery absorber of oxygen. Or it could be disequilibrium chemistry. That's also a problem that can mess around with your oxygen. So this is a big, gigantic warning sign I want to put out there about C to O ratios for these objects. Clouds, clouds, clouds. Yeah.
This suite of retrievals, were they a bunch of different codes?
Yeah.
It's not like one code might have a problem, it's a bunch of different codes all agree that there's an overabundance of
Yep. This is at least 3 different codes. I think there might be 4 codes in here where different approaches in some ways, like the retrieval frameworks, are all slightly different. They were actually, all the ones that were used in brown dwarfs were all calibrated to each other because everybody retrieves the same object. It's called Gliese 570D, and you make sure you can do that object correctly, and then they go to town on whatever object they want to do. So there's definite consistency amongst the codes here. All right, clouds, part 2. What's the deal with these clouds then? So is there enough information in the observables of brown dwarfs or planets, whatever you want to call them, I'll just call them worlds probably from now on, to confirm the presence of clouds and to determine the cloud composition and weather patterns? And this is where our objects are just such winners. But before I talk about that, I want to show something off. What are the clouds made of? This is a day in the life of a scientist that works at a museum. This is a picture from the Hall of Gems and Minerals in the American Museum of Natural History. Has anybody ever been there? Oh, 1, 2, 3, 4, a couple. Great, wonderful. Dave, you don't have your hand up. That's too bad. This place is our recently renovated Hall of Gems and Minerals. You should definitely visit. It's really, really beautiful. You can walk around, and if you do exoplanets or exoplanet atmospheres or brown dwarfs and brown dwarf atmospheres, you're literally walking amongst the kinds of things that are in your clouds. There's a whole case dedicated to quartz, silicon dioxide, and all of its various forms that it comes in. There's a whole cart of things in here on the inosilicates, and you get your phosphorite and your enstatite, and your quartz is all over the place. And then we've got pyroxene and olivine, and all of these are forms of the clouds that we find in the atmospheres of our objects. And the big thing in all of them is this oxygen. There's a lot of oxygen in these clouds. So back to the brown dwarfs. What is our observational evidence that the clouds are actually there? Well, this is a plot, pretty famous brown dwarf type plot, from the M-type brown dwarfs all the way to the T-types on the x-axis, and then the color, the near-infrared color, with redder objects up here, bluer objects down here. You see the objects get redder. They kind of peak by the mid to late type L dwarfs, and then they get bluer and bluer and bluer into the T-type objects, with the theory that this is the onset of clouds, condensate clouds, those quartz-type clouds, enstatite and phosphorite, and all of them were coming in and then clearing out through the T-dwarfs. That's one piece of observational evidence that we had for them. The other piece is within the spectra, and this is where the strength of brown dwarfs really comes in. This is a spectral energy distribution library about to be blown open by JWST data that's going to fill in the part that we could never really fill in from the ground, which was this area in here, which was always kind of hard to access. And this is a lot of information from optical all the way out to well into the mid-infrared. And if you narrow in on this one little section here, between like 7 microns and like 13 microns, there's a real spectral feature there. It's silicon grain absorption. So here's a zoom in on one particular object called 2MASS 0355. And this big jump down and across here that looks almost like an elbow coming down is the signature of silicon grain absorption. All of those beautiful things in the Hall of Gems and Minerals that I just showed you, those are all silicate species condensates that we find across our great planet. We find those same grains, you find these in debris disks as well. We find them in the spectra of these objects that we suspected were very cloudy. They're not in all of them. This is another example, 2MASS 1507, another L-type object that does not show that same strong feature. I'll just blink them so you can see how that elbow really changes. But that is the signature of the silicate absorption, a sign of clouds. Now, a new postdoc in my group, Gennaro Suarez, pictured here, Gennaro did something, I think, pretty phenomenal, which is he grabbed everybody's Spitzer IRS data from the brown dwarf community, 113 objects across like 40 different proposals or something, maybe 30 different proposals, re-reduced all of it, and created a silicate index to demonstrate how that silicate feature changes with temperature, as well as a couple of other features in the brown dwarf. So now, from the x-axis here, from late type M dwarf all the way to late type T dwarf, this is the x-axis, and on the y-axis is showing you a measurement of that silicate feature using Gennaro's defined index. And you can see, similar to how it worked for the colors that I just showed you photometrically, that silicate index increases, strengthens through those L dwarfs, and then drops down through the T dwarfs. It doesn't completely disappear, though, indicating that you still have clouds in the T dwarfs. I'm going to zoom in on two of them in particular right now, SIMP 0136 and 2MASS 2139, two very famous brown dwarfs / exoplanets, hard to say. These are really hard to define objects. I'm going to zoom in on these objects for a very good reason. You can see where they are. They're down here. They don't have a huge silicate index representation like you see up here. So just keep that in mind. I'm going to show you some of these guys. I'm going to show you how we really, really dug into the clouds for these two objects. So this is going to be work that's recently led by another postdoc in my group, Johanna Voss. SIMP 0136, very famous, early type T dwarf that Jonathan Gagne, myself, several years ago discovered that it was part of a 200 million year moving group called Carina Near. About 2 years ago, we also discovered that this second object, 2MASS 2139, both of these very famous brown dwarfs because of how variable they were. If you looked at their light curve, you saw they had very high amplitude variation and a rapid rotation. Both of them are listed here. SIMP 0136 has a rotation period of 2.4 hours. 2MASS 2139, 7.6 hours. They're both about 1200 to 1300 degrees Kelvin. Early type T dwarfs, both in this 200 million year group, masses 10 to 20 Jupiter masses. They're both equator on. That's going to be important in a second. So we decided let's retrieve them and look at their chemistry. Why are we going to go after these two? They look variable. They definitely have clouds. They're in the same moving group. So we don't have to worry about some weird thing like metallicity differences or initial condition differences between them. So we did the same spectral inversion technique. SIMP 0136 is here. In black is the data, and overlaid in green is our retrieved model. I've marked off, again, the absorption features that are prominent in here, water, methane, and you can see how well fit that retrieval is on this source. Zoom in on that silicate feature that we were able to fit with our retrieval, and we threw a kitchen sink of models at this thing to try and figure out what exactly the bulk chemistry was going to be. We did the same thing for 2-mass 2139, and in black was the data. We didn't have as much data on this object because their simple 136 had a Cari data, which fills in this like 3 to 5 micron area that's just very hard to get. But once again, we had a very good fit from the retrieval. We independently threw a kitchen sink of models at this object, and we found the following. Both objects, we were able to best fit with a cloudy, patchy, phosphorite cloud over an iron deck cloud. We put an iron deck cloud down, we got a patchy phosphorite cloud above it, we know that they're variable objects, and then we were able to constrain more gases than we were with the T-dwarf because we had more data: water, CO, CO2, methane, ammonia, sodium and potassium, chromium hydride, iron hydride, and silicon oxide. All of these were constrained with our retrieval model. Independent kitchen sinks thrown at both of them, and they both came up with the same best fit model. Really nice thing about retrievals is that this is our phosphorite, patchy phosphorite cloud over the iron deck cloud, is that you can get to the TP profile, the temperature on the x-axis here, versus the pressure on the y-axis here. The black line coming down here shows you the TP profile for our source, our best fit, with the 1 and 2 sigma contours in pink, and then overlaid in yellow, green, and teal are the grid model self-consistent profiles. So the good thing here is that it's not isothermal. It matches well to what the grid models might predict, but you can see it's more flexible. It's a bit warmer than one would have expected up here, but it fits pretty well in here, which is kind of through the photosphere. Now, we were able to place where those clouds might be: a deeper iron deck cloud and a higher lying patchy phosphorite cloud on top. Fully parametrized objects. And we looked at the chemistry for these objects for which we were able to solve the clouds really well, and we backed out the C to O ratio, and they came out as solar and matching each other. So in this way, one of the things I would conclude is that when we do a really good job of solving for the clouds, we've figured out where the oxygen is, and we're able to solve well for the C to O ratios for the objects, as opposed to Gliese 229b and that suite of T-dwarfs, where I don't think we're fitting the clouds very well at all. We also don't have the full extended data like you have in the cases of these objects. But an important part of these two objects is that there are differences between them. They do have about the same cloud coverage, which was very exciting, about 70% cloud coverage for simple 136, 83% cloud coverage for 2-mass 2139. But H2O and CO were a bit off for both of them with each other. And we think, and that's how the metallicities look quite different between the two of them. We think that, we're speculating on this, simple 136 is a known auroral emitter. And Greg, who's here somewhere, is the one that led work on simple 136 being an auroral emitter. 2139 is not. So one of the things that we've been speculating is whether auroral emitters are going to have different amounts of hydrogen, and that it's not the O or the C that's the problem in this case, it might be the hydrogen. Important prediction that comes from this ability to retrieve an object this well with the clouds constrained and all the fundamental parameters constrained is a prediction that you can make. So both of these objects, simple 136 and 2-mass 2139, have been monitored with the Hubble Space Telescope, and they are both variable. In black, it's showing you what the HST variation is, and in blue is showing you what our retrieved model parameter prediction was for the variability amplitude across wavelength. And we were able to successfully predict with our retrieval, completely independent of the HST monitoring, what the HST monitoring would see, the variability amplitude of that HST monitoring. We were also able to basically successfully predict what the variability amplitude should look like at both Spitzer 3.6 and 4.5 microns. Both of these objects were monitored by Spitzer. So we've successfully predicted that through the retrieval. And we predict that there's going to be a strong signature of variability in that silicate feature if you were to say, for instance, propose to use JWST to monitor with MIRI. So prediction here of what you'll be able to look at if you want to study these clouds in more detail. All right, important note on these clouds too. So clouds show a lot of variability here. This is just a beautiful animation from the SIMPO 136 papers. Variability showing you the light curve and maybe a simulation of what one of these objects looks like. In like several years ago, I led a Spitzer proposal for about 600 hours to monitor several young brown dwarfs. And we were able to determine that young brown dwarfs are more likely to show variability than older equivalent temperature objects. That's really important because variability plays a pretty strong role in cloud-related observables. We have recently put together a picture that uses this variability sample alongside the silicate index that I think is kind of astounding in some ways, and that's the following. Viewing angle also plays a critical role in cloud-related observables. So here's a picture of Jupiter. This is Jupiter pole-on from the Juno mission, and this is Jupiter equator-on from the same Juno mission. If you're looking at Jupiter pole-on versus equator-on, you're looking at clearly a very different looking object. So how does that inclination angle affect your observed parameters? So this is a paper that that Gennaro is going to lead very soon, and it's because we kind of discovered it the other day. This is a very hard plot to make because you have to have mid-infrared spectra in order to measure the IRS silicate index. So you needed Spitzer to put things on this plot. You need to be able to measure an inclination angle for a source, which means you have to have a rotation rate and a V sin I. So you have to have high resolution spectra, and you have to have monitored it, and it had to be variable in order to check how that silicate, that ability to really dig in observationally to your clouds, might be impacted by the inclination of the system. And we've discovered the following. Here's an object down here on the bottom that's basically pole-on or closer to pole-on with a very low silicate index. Object that's equator-on, way up here. So nearly equator-on, very strong silicate index, and a sample of other objects that fall in between. And they're color-coded by that J minus K color that I was showing you earlier is one of our early indications that observationally you have a cloud. We never see trends in brown dwarf science, ever. I mean, this is a very clear trend of inclination angle is going to make a big difference in your ability to parametrize and look at those clouds. So, gigantic warning sign in some ways on this. Yeah.
So earlier you showed this trend with the index and the spectral with brown dwarf. How does this interface with the inclination?
Yeah, so I should note that this set of objects that are on here are the same temperature. So all of these are mid-type Ls. They're basically close to the peak of that silicate index area. So between like L3 and L6 is what's on here. Because temperature will really play a role, but you're going to see the same thing. It's just going to change with temperature to a lower and lower angle, but you'd still see the same trend. At least that's our prediction. All right, last part of this, which is on JWST. This is an image from a planetarium show that I gave the other day featuring everybody's favorite, well, my favorite, maybe other people in here's favorite, new telescope, JWST, showcasing things that it's looked at. And first case is that we're already digging into some amazing science with JWST on this exact thing. This is a paper released recently. Brittany Miles led this paper. It's on the archive. It's by the whole JWST ERS team from direct imaging. It shows you this gorgeous spectral energy distribution from 1 microns or just shy of 1 microns all the way out to almost 20 microns. Everything you're seeing in here is real. Every bump, every wiggle, all of it, it's real. It's real features, real data, rich data. If you look carefully in the 7 to 13 micron area, you'll see this object has a very clear silicate cloud, silicate index, we're calling it a silicate cloud, but right now it's just the silicate absorption feature because we haven't figured out the cloud yet. Very clear on this. However, this is a lot of data, and I have a postdoc on my team, Niall Whiteford. He's leading the retrieval analysis of VHS 1256b for the ERS team, as well as for a XRP proposal that I've got in, and it's very hard. This is a warning. We cannot computationally handle the resolution of JWST yet, and the spectral coverage is also overwhelming. So we have to resolve it down to Spitzer data right now and resolve it down to specs data right now. It seems a little sad, but it's not that sad because we are gonna get there. But in order to get JWST to work and be able to do all the great science people want to promise, I think you have to learn from what we were able to do with the brown dwarfs first. And then we can step into the higher res data. All right, last part of this is the brand new data that I can show you that is not published yet. And that is, the last part of this is on the coldest objects. So chemistry, we can definitely extract, but you have to move in with a C to O ratio warning that you're gonna have to attack the clouds if you're gonna claim your C to O ratio in a companion system, even an isolated system. So in order to attack the clouds, you really need that longer wavelength data with that silicate feature. But then when it comes to the coldest objects, which are much more akin to Jupiter, I think we're kind of also screwed a little because they are extremely diverse. So how will we deal with the diversity of cold worlds? So I'm going to show you the last thing here, which is data from our JWST Cycle 1 proposal to demonstrate for you the objects that we chose to go after to characterize. I'm going to show you a famous diagram for cold compact objects, which is a Spitzer near-infrared color from bluish color to reddish versus the absolute magnitude at Spitzer's channel 2. And show you how spread out some of the objects are. And I just want to say this is an extremely hard plot to create. This took an enormous amount of effort from many people and a workhorse of the Spitzer Space Telescope to be able to get parallaxes for all of these objects. So we can even place them on this plot so I could show you how diverse they are. So these are the warmer of the objects, or the T-types, down into the Y-types here with this crazy object down here called WISO-855, which is the 250-degree Kelvin object. In our JWST proposal, we split this color magnitude diagram up into 4 bins, and we've targeted all of the objects that have the circles around them, deciding that we could get a spectrum of the normal objects that run down the center, and then the ones that were crazy bright, as well as the ones that were crazy faint for their given temperature bin. And what I'm going to do is show you the data for 3 objects. Some of them just came in. This is all data that's just like freshly acquired. You're also just going to hear me speculate on what I think is happening. I'm going to show you data from this object, WISE 0415, which is the warmest one, or so we think, and the bluest one. I'll show you the colder one that we have. It's called W1935. And then I'm going to show you an intermediary one. Okay, ready to see some JWST data? It's high res. It's high res. It's got a lot going on. Okay. 0415 is first. Yeah, so we had to break it into 3 panels. We chose to go for the peak of the spectral energy distribution, and we chose to go after the high resolution lines that we could back out to really dig into the chemistry. Every wiggle in there is clearly real. Overlaid in blue is a model for what we think should have happened at a 600 degree Kelvin object with a log G equals 5 with non-equilibrium chemistry. It fits pretty well. Pay attention to this harmony of CO in here. Now I'm going to show you, this was our bluest, warmest object. Now I'm going to show you what should look like a very different object, which is our coldest object in the sample. Okay. That's the cold one. Warm one, cold one. When I first plotted them, I thought they were the same object. I was really annoyed. I thought, did I just overlay the same object? Because they look on, and now I'll show you the intermediary object, 0535. Very, very different object. What the actual F is going on. I showed you this one, which looked almost identical to this one, and then this one in between looked totally different. So, welcome to the new world of weird chemistry driving these Jupiter-like objects. It kind of seems that 0535 has like smushed lines a little bit, like they look a little smushed maybe, which, again, this is speculation. But now we're speculating that maybe this thing is covered with some crazy cloud, and that's causing it. But we're lost in speculation land right now. So, yet to be seen. You can see from this plot, we have a lot more objects to come. This one is up next. This should come any day now, and I think it's going to be very telling when that spectrum shows up. Because if it ends up looking like this one, I don't know, I'm going to throw my hands up. Give up, walk away. They could all just be variable. All right, these are my conclusions. I gave you chemistry. We still have quite a bit to learn about this C to O ratio. Brown dwarfs with retrievals, they trend towards supersolar values regardless of if an object is a companion or isolated, so we have to be very careful before we say C to O ratio is the holy grail of saying whether something's a brown dwarf or a planet. It either indicates a mystery oxygen absorber, aka in a cloud, or a flaw in the retrievals approach, or a disequilibrium chemistry problem. Clouds, 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 solve the clouds. You need the mid-infrared data to constrain the cloud properties. Once you have it, you can differentiate between the kinds of clouds that you might have. And then just that part 3 is just diversity. I just wanted to say also, I wasn't able to give shout outs to everybody in my team, but I just want to show you pictures of our little crew in New York City. We're a great group. And anybody that visits New York, you can come visit the American Museum of Natural History and come to that Hall of Gems and Minerals. I'll leave my conclusions up and take any other questions you guys have.
Wonderful, thank you. Questions for Jackie? I'm going to start with an easy one. Ben's dog. Tell me it's some kind of retriever.
It is a lab, yeah. Sometimes I'll show the picture of the lab. The dog's dead, so all we've done is seen a picture. It's the dog he grew up with, so he just really loved it when he was a kid.
It's a memorialized dog.
It's not like it died during during retrievals. Yeah.
So going back to the C to O ratio, in the moving group pair that you showed,
Yeah.
the C to O is very similar, but you showed there were some other differences, including oxygen.
Yeah.
Oxygen was really different, and you didn't follow your own advice. You didn't put carbon on that one.
It's just because I ran out of space on there. We do have the carbon and they match. Yeah.
So it's really, again, coming back to the oxygen.
Yeah.
So if you're saying that an oxygen difference, you think from the first part is due to clouds,
Yeah.
but in the second, in that pair, you're saying the cloud properties are very similar, then
Yeah.
how is that tied to different oxygen?
Because CO is, well, I agree. This is a little bit of a problem we have in that particular case. I'll show it to you again. Because the C, it's not as bad as the H2O in that particular case. This one, yeah. It's not as bad as the H2O being problematic. I mean, you can see it's minus 3.6 versus minus 3.24, minus 4.03, minus 3.84. I mean, they're off by a bit. They're both off by a bit. I don't know exactly why this is off by as much as it is, because there's oxygen in both cases, in both the H2O and the CO. The other important thing to realize here is that you don't actually get to measure the C to O. You end up measuring where you think most of the carbon is and where you think most of the oxygen is. And so in this case, it's usually the most of the oxygen is in the CO2, and then methane is where you get all of your carbon from. So the oxygen's in your CO2, and then the most of the carbon comes from CH4. So because of that, it's more of that ratio that becomes important. But yes, problematic. Didn't say we solved everything. We came close.
For that set of cycle 1 brown dwarfs, are you going back to any of them to see the variability?
We don't know if those are the cycle 1 brown dwarfs that are at the end of the talk. These we don't know if they're variable or not. So these are all, this is a well-known brown dwarf. I don't think that anybody did Spitzer on this one. There is an unpublished amount of Spitzer variability that Mike Cushing keeps promising that he's going to publish, that is on a couple of the Y-type objects that would tell us about the variability of those particular objects.
Sure. If you had to put money on it, if you went back to this object again with JWST in a year, do you think you'd get the same spectrum?
I think so. I don't think it's a variability thing in this one. I think this is, the problem, this one, 1935 and 0535, 1935 is a fairly new discovery. Fede, who's here, was one of the lead authors on, this was discovered both by the Backyard Worlds project and Catwise project that was based here at IPAC. So no one monitored this thing. Like, they're brand new. These brand spanking new objects that JWST was able to look at. And 0535 is also fairly new. I don't think this was on any Spitzer either. I don't know. This is the one I'd want to monitor. These two, they just look clean. Or maybe they don't. I don't know.
So how many cycles into JWST do we have to get before we're starting to ask for, like, give me 40 hours staring at this brown dwarf so I can monitor it?
I mean, I think that's next cycle. I think we're asking for that in cycle 2. Because I think we have enough evidence, especially for the silicate feature. We could go after that silicate feature like crazy. It's going to vary, and it's probably going to tell us a lot about what the clouds are doing. From the warmer, these guys don't have silicate clouds the same way. These are cold objects. They have salt and sulfide clouds and water ice clouds. And so there's going to be other features for them. We dipped into the cold Jupiter-like objects here. So they're different. Still diverse and interesting, though. Yeah, well, we started Backyard Worlds, Planet 9, because we wanted to find more of these cold, old, brown, well, old, young. You could have a young ejected planet. Could you have a 1 Jupiter mass object that's just sitting out there? There's no reason to rule it out. It could happen. There's a group at IPAC led by Davey Kirkpatrick, who's here, and it's funded by NASA ADAP, and it's to look for the 20 parsec sample to just completely define it so that you can get the mass function down to the bottom. Like, what is the basement of star formation? Because 20 parsecs is a volume that you could probably count most things up on. And once you do that, you're able to actually say, where's the bottom of how many of these cold things can you expect? I think we still have a question mark as to what the basement is. But with Backyard Worlds, we've been trying to find anything that was missed previously. And we really dug through the garbage to try and find anything that had been missed by previous surveys that were looking for cold, isolated, a couple Jupiter mass objects that are just hanging out. Because is it possible that there's one closer than Proxima Centauri? Sure, I don't see why not. They're easy to hide. They're very easy to hide. They're cold.
Is this something that the Roman microlensing bulge survey will get at all? A population of smaller brown dwarfs?
Well, so the problem, Roman is optical, optimized. And we need, these things are bright in the mid-infrared. What you need is infrared Gaia.
This would be through microlensing of background stuff.
Yeah, so Davey worked on this idea a bit, and I mean, I think it's possible to find objects that way, but I think that's kind of more of a needle in a haystack. It feels like it'd have to be against the background, like you'd have to find it towards the galactic plane because you need the background of a crowded area. Not impossible to say you could find one, but the idea would be scan the whole sky, do the whole sky and find it that way.
Question about the C/O ratio again and hiding oxygen. So the way you back out C/O ratio, just kind of clarification question. You measure a C/O abundance and some sort of infer that there's some sort of cloud, and then you use kind of equilibrium chemistry to say this is how much cloud oxygen we have based on a muting cloud feature.
Yeah, so this is the complicated nature of trying to, once you get your C/O, you get an atmospheric C/O, and then you have to go to the bulk C/O. And everybody uses the same technique, which we now think is flawed, which is that in 1997, Burroughs and Sharp wrote a paper that described how much oxygen sequestering that you could get at these temperatures. And we use their prediction for oxygen sequestering. So the values are actually quite a bit higher. I'm showing you the corrected C/O ratios for that sequestered oxygen. That's why we work closely also with the chemists, with Shannon Vischer, to try and understand why does it seem like those values are so far off, because our values are still so high even after we use what was supposed to be state-of-the-art estimations.
And a follow-up, so you showed that viewing angle has a lot to do with this, and cloud composition. Could that range in C/O be something about viewing angle, or do you think it's more something about the actual differences in these objects?
Yeah, so the thing with this, the viewing angle, I showed you viewing angle versus the silicate feature. And that silicate feature is showing you the strength of the cloud. Could it mess with the best retrieved model? It probably could, but it's still unclear how that would change both carbon and oxygen values. I'm not totally, we've talked about this a lot recently, because that plot's new. It's not published yet. You could tweet it, I guess, but don't. That's new, showing how severe that difference could be. And now we're we need to retrieve the object, the pole-on object versus the equator-on object, and make sure that they stay consistent with each other. So we're working on that to make sure we fully understand the difference between what that introduces into our C/O ratio differences. I'm more concerned about how cloudy you think the object is. That's our new thing. In seeing, people just thought, for instance, the objects at the bottom there were just not cloudy at all. Pole-on object just didn't have clouds or something. But not the case. They're just pole-on. Yeah.
One more question, Phil?
So another question about the viewing angle thing. Is it just because the clouds have a geometry where they're in bands, and you see less of the cloud if you're full on?
Well, you can see, part of why I show that visual with Jupiter is because it's so clearly, visually appealing to see Jupiter's pole-on versus equator-on. And, staring down the barrel you have a thinner cloud layer towards the poles. You do get thicker bands that are towards the equator. There could be other things involved with pole-on versus equator-on as well. Like auroral emitter things are probably playing a role. I don't know what yet. We need people to do more auroral investigations of these objects. But this is a notable thing in solar system objects too, of looking at Saturn pole-on versus Saturn, like that's got that crazy hexagon structure at the pole of Saturn, you know? It's not surprising to us that this is the case. And there were people that made predictions that, hey, maybe inclination angle is something we should be paying attention to back in the day of early brown dwarf studies. And what I'm also suggesting is for exoplanet studies, which are fantastic, but always seems like they lag a little bit behind the work that we're able to be like, oh, maybe you guys should pay attention when a rapid rotator versus a slow rotator. Maybe we need to figure out equator-on versus pole-on before we go too crazy on our cloud properties, because you're going to come up with real different conclusions about a source if you don't know the orientation.
Okay, let's thank Jackie again. Thank you.